topology usually consists of a single cable on which computers attached to the ends of a bus network require a terminator to prevent signal echoes. Because all computers attach directly to the cable, any computer can send data to any other computer and all computers will receive the signal. The computers attached to a bus network must coordinate to ensure that only one computer sends a signal at any time. Bus networks are relatively inexpensive and easy to install for small networks. Ethernet systems use a bus topology. The main advantage is that it is easy to connect a computer or device and typically requires less cabling than a star topology. One disadvantage is that a break in the cable will bring down the entire network. Ring topology arranges for computers to be connected in a closed loop. A cable connects the first computer to a second computer, another cable connects the second computer to a third, and so on until a cable connects the final computer back to the first. The name ring arises because, as one can imagine, the computers and cables connecting them are arranged in a circle, as this figure illustrates. In practice, the cables in a ring network do not form a circle. Instead, they run along hallways or rise vertically from one floor to another. Ring topology requires a computer to connect to a small device that forms the ring. This is needed for the ring to continue operation even if some of the computers are disconnected. Ring topology is most commonly used in small networks such as in schools, offices, and small buildings. Mesh topology. The mesh topology connects each device to every other device, thus providing a direct connection between each pair of computers. This provides great redundancy. The chief disadvantage of a mesh arises from the cost. The number of connections needed for a mesh network grows faster than the number of computers connected. So these connections are expensive, so few LANs employ full mesh technology. In star topology, all computers are attached to a central point. The center of a star network is often called a hub. A typical hub consists of an electronic device that accepts data from a sending computer and delivers it to the appropriate destination. In practice, star networks seldom have a symmetric shape, nor is the hub located at an equal distance from all computers. Often, a hub resides in a location separate from the computers attached to it, such as in a wiring closet. For example, computers that reside in individual offices while the hub or switch is in a location accessible to the organization's networking staff, like the wiring closet. Large and small networks use the star topology where all nodes are indirectly connected to each other through one or more switches. The switch acts as a central point through which all communication passes. Why do we need so many different topologies? Each of the local area network topologies have their own advantages and disadvantages. A ring makes it easy for computers to coordinate access and to detect whether the network is operating correctly. However, an entire ring network is disabled if one of the cables is cut. A star helps to protect the network from damage to a single cable because each cable connects only one machine. A bus requires fewer wires than a star, but has the same disadvantage as the ring. The network is disabled if someone accidentally cuts the main cable. A mesh provides redundancy, but is expensive to implement and seldom implemented. Regardless of the topology used on a local area network, we have to identify packets sent on the local area network. Each user sends out packets of data, but how are the destination addresses of these packets identified? The IEEE has created a standard for packet identification. Each packet that travels across the shared medium is intended for a specific recipient, and only the intended recipient should process the packet. Demultiplexing, which means to separate, uses an identifier known as an address. Each device is assigned a unique address, and each packet contains the address of the intended recipient. In the IEEE addressing scheme, each address consists of 48 bits called a Media Access Control Address, or simply a MAC address. Networking professionals often use the term Ethernet address, but this address also is referred to as the network interface card address, hardware address, physical address, or even burnt-in address. The IEEE allocates a unique address for each interface device by ensuring that every network interface card, every NIC, is assigned an exclusive address when it is manufactured. Rather than assign individual addresses, the IEEE assigns a block of addresses to each equipment vendor and allows the vendors to assign a unique value to each device they manufacture. Thus, a 48-bit address is divided into 3-byte organizationally unique ID, an OID, that identifies the equipment vendor, and a 3-byte block that identifies a particular Network Interface Controller, NIC, as shown in this figure. The OUI is assigned by the IEEE, and the NIC is assigned by the manufacturer. The manufacturer assigned a different number to each NIC it manufactures to ensure that every NIC worldwide is assigned a unique MAC address. IEEE addressing supports 3 types of addresses which correspond to the 3 types of packet delivery options. Unicast is a single computer communicating with a single destination. Broadcast is a communication to all computers in the network, while multicast is communication sent to a subset of devices in the network. This table provides a summary. The 2 low-order bits of the most significant byte of the OUI are assigned a special meaning. The least significant bit of the most significant byte is a multicast bit that specifies whether the address is unicast, 0, or multicast, 1. The next least significant digit represents whether the OUI is globally unique, 0, or locally assigned, 1. Global are assigned by IEEE, and locally are available for experimental work or for organizations that desire to create their own address space. This formatting of the MAC address is displayed in the figure. It may seem odd that the IEEE address format reserves a bit to distinguish between unicast and multicast, but it does not provide a way to designate a broadcast address. The standard specifies that a broadcast address consists of 48 bits that are all ones. Thus, a broadcast address has the multicast bit set. Broadcast can be viewed as a special form of multicast. Each multicast address corresponds to a group of computers, and broadcast addresses correspond to a group that includes all computers on the network. Recall that the sequence Ethernet bits are transmitted. It sends the most significant byte first and the least significant bit. So the unicast multicast bit is the first one received by the NIC. Broadcast and multicast addresses are useful in local area networks because they permit efficient delivery to many network computers. To understand the efficiency, recall that a LAN transmits packets over a shared medium. In a typical LAN, each computer on the LAN monitors the shared medium, extracts a copy of each packet, and then examines the address in the packet to determine whether the packet should be processed or ignored. You can relate multicast as receiving mail in your name or as a member of an organization such as homeowner, safe driver, or even occupant. Framing refers to the structure added to a sequence of bits or bytes that allows a sender and a receiver to agree on the exact format of the message. Although words are made up of individual bits or bytes, we don't just send a character or a byte at a time, but a package, the communication stream during transmission. In synchronous communication systems, the concept of framing is used as a mechanism that allows a receiver to know where a message begins and ends. In more general terms, framing refers to the structure added to a sequence of bits or bytes that allows a sender and a receiver to agree on the exact format of this message. In a packet switch network, each frame corresponds to a packet. A frame consists of two conceptual parts. First, a header that contains a metadata, which is the information used to process the frame. The term metadata refers to information about the data contained, sometimes referred to as data about data. The second part of the frame is a payload, which contains the data being sent. Typically, the payload is much larger than the frame header. A message is opaque in a sense that the network only examines the frame header. The payload can contain an arbitrary sequence of bytes that are only meaningful to the sender and receiver. Some technologies delineate each frame by sending a short prelude before the frame and a short postlude after it. We need to mark the beginning and the ending of a frame. In this example, let's assume that a packet header consists of 6 bytes, while the payload consists of an arbitrary number of bytes. We can use the ASCII character start of header, SOH character, to mark the beginning of a frame and the end of transmission, EOT. That's at the end of the frame. ASCII, ASCII, stands for American Standard Code for Information Interchange. In the ASCII character set, the SOH has a hexadecimal value of 01, and the EOT has the hexadecimal value of 04. An important question arises: what happens if the payload of a frame includes one or more bytes with the value 01 hexadecimal or 04 hexadecimal? The answer lies in a technique known as byte stuffing that allows transmission of arbitrary data without confusion. Here's how it works. To distinguish between data and control information, such as frame delimiters, start and stop bits, the sender changes the data to replace each control byte with an added sequence. This added content is understood by both the sender and the receiver. When the receiver places control bits with original data bits, as a result, a frame can transfer arbitrary data, and the underlying system never confuses data with control information. The technique is known as byte stuffing. It is also called data stuffing and character stuffing. As an example of byte stuffing, consider a frame as illustrated in the table. Because SOH and EOT are used to delimit the frame, those 2 bytes must not appear in the payload. Byte stuffing reserves a third character to mark occurrences of reserved characters in the data. For example, suppose the ASCII character ESC, which has a hex value of 1B, has been selected as the third character. When any of the 3 special characters occur in the data, the sender replaces the character with a 2-character sequence. The sender replaces each occurrence of SOH by the 2 characters ESC and A, each occurrence of EOT by the characters ESC and B, and each occurrence of ESC by the 2 characters ESC and C. Each receiver reverses the mapping by looking for ESC followed by an A, B, or C, and replacing the two-character combination with the appropriate single character. The figure shows an example payload, and the same payload after byte stuffing has occurred. Note that once byte stuffing has been performed, neither SOH or EOT appears anywhere in the payload.